Ooh, alright. I should be live. So we're going to give this 15 seconds to start, and we're going to make sure that my voice sounds reasonably okay so that we can get the stream started. So we are just waiting for it to kick in, but this will be a video stream. Alright, it's a little too loud. We're going to do it like that. This should work fine. Alright, so this is a video of the Rossmann repair training guide created by Louis Rossmann, open source to the internet. I'm about to put everything on screen. But he finally released what he gives off to his classes to the open internet. So we are just going to take advantage of it. And I'm going to stream as I learn his stuff as we go. Let me switch over scenes here. I think it's this one. Nope, not that one. No, yeah, it is that one. There we go. So now you'll be able to see exactly what I see. Rossmann Repair Training Guide, created by Louis Rossmann, open source to the internet. YouTube link. You can read more about our company and inquire services here. We have a paid forum to provide support and component level technicians. There's the forum. Go out for training at our store, one-on-one. There it is. I looked at it, it's like $120 an hour, so if you pay $1 for every 30 minutes for Lewis's time, it's worthwhile. Never gonna do it though. Can't afford his genius. Alright. The biggest problem in this business. Engineers know how to repair logic boards. Engineers do not want to fix logic boards. Regular people want to fix logic boards. Regular people are not engineers. My anxieties have anxieties. You need not to know how to a resistor resists. You need not know how an inductor creates inductance. You need not know how to create a circuit to repair common faults. We are not going to spend 4 years turning you into an expert on physics, chemistry, and electricity. We'll be skipping a lot and getting to the point. Alright. 4 slides blank. Makes it easy. Electricity is based on theft and burden. You're lazy. You don't want to get up. Amen. Imagine if I stole your wallet. You'd probably chase me around the room. To get you to get off your ass, I motivate you by causing a pain point. Fair enough. Electricity works the same way. Stealing an electron from an atom gives it a positive charge. Giving an atom an extra electron gives it a negative charge. That sounds backwards, but we're going to go with it. Stealing an electron from an atom gives it a positive charge. So if it has less, it's positive. Giving an atom an extra electron gives it a negative charge. Okay. The more electrons you steal, the higher the charge. The higher the charge, the higher the voltage. This is kind of making sense. To get electricity to do anything, we manipulate it. What will you do to get your phone back? What will the atoms do to get their electrons back? What will Jessa do to not fix 100 iPad minis with BGA problems within a no-fix, no-pay business model? What will atoms do to toss out unwelcome, uninvited electrons? This is what we are doing to electricity. Alright, that makes sense. Electricity would be the elephant or the rabbit, and the carrot and the peanut should be the atoms, I believe. We show it a path that it wants, and tell it, if you walk through this path, you'll get what you want. We rarely give it what it wants. If we did, our stuff would turn off. Yep, makes sense. Just as the elephant walks to get the peanut, electricity goes through anything to get to ground. Oh. So 120 volts, that's the US wall outlet. Light bulb is on. Ground. The 120 volts wants to get back to being 0 volts. It doesn't like being 120 volts. That makes sense. The electrons wish to flow back to 120 volts. But in order to do so, they must first go through the light bulb. The light bulb turns on as electrons flow through it. Alright, that makes sense. We're going to check my stream real fast. Alright, cool. Stream still looks good. Ooh, I didn't mean to go. Yeah, but it should be 120 ground on this side. So it's 120 before it hits the bulb, but because the bulb uses all the electricity, it goes back to ground. That's not exactly how it works, I think, but this makes, I can understand this. If 120 volts is applied to the light bulb, but there is no path to ground, it won't light. 120 volts, the light bulb is off because there is no ground. It's just an open wire. Just as the elephant has no motivation to get up without the peanut being dangled, a voltage won't cause electrons to flow without a complete circuit. Just because we apply 120 volts to the light bulb does not mean it will turn on if we do not complete the circuit by adding a ground on the other end. Woo! That is a long sentence with no... Oh, it's two sentences in one comma. How do we measure this? Voltage. Think of this as a person's strength. Boom. Current. Think of this like stuff actually moved using one's strength. Resistance. Think of this like the weight of what we are moving. A 1,000-pound bag is more difficult to move than a 10-pound bag. That makes sense. Ohm's law helps you figure this out. Use an Ohm's law calculator online, or an app on your phone. Your 4th grade teacher told you you won't be carrying around a calculator everywhere for the rest of your life. They lied. I'll agree on that one. How does this work? Power is equal to voltage times current. 2 volts at 10 amps equals 20 watts. That makes sense. Current sent through a circuit is equal to voltage divided by resistance. Resistance in a circuit is equal to voltage divided by amperage. This is called Ohm's law. Alright, we got a couple pies here. So volts is V, amps is I, ohms is R. Resistance, I don't know what the I stands for, voltage. So amps times ohms equal volts. I would think that's what this means. We can come over here and find out real fast. So amps I, volts is V, power is P, ohms is R. So let's see, which one would this be? This is volts. So we need to find, here it is, yes. So volts equals amps, which is I, times R, which is ohms. So if we want to find here we go. Volts times amps equals power. And I think power, he means as watts. I think watts and power are the same here. So if we have power divided by volts equals amps. That makes sense. Yeah, because that's the exact other way here. Where the power divided by amps equals volts. So yeah, power is watts. I know what you're thinking. At 10 a.m. To keep it simple, more resistance equals less power. Duh. Less resistance equals more power. Duh. Higher voltage equals more power. Duh. Lower voltage equals lesser power. Duh. That all makes sense. Alright, make sure I can still see myself. Example, speaker amplifier. The Rodal RB-1090. Lower resistance equals more power. The same amplifier can put out almost twice as much power when a lower impedance speaker is attached. Specifications. Continuous power output 20 through 20 kilohertz. Less than 0.03%. Alright, I do not understand this part. 380 watts channel into 8 ohms. 700 watts channel into 4 ohms. Maybe it'll make sense on the next slide. This part I do not understand. You do not set current. You can increase voltage to increase current. You can decrease voltage to decrease current. You can increase resistance to decrease current, and you can decrease resistance to increase current. That all makes sense. I do understand this one. Let's check out a real-world example. 120 volts, so we're plugged into the wall. 2,000 ohm light bulb. The light bulb is on but very dim, and then ground. Voltage is 120 volts. Resistance is 2,000 ohms. 120 volts divided by 2,000 ohms equals 0.06 amps. So we are going to go back real fast, and we're going to find this thing. So if we have volts and ohms, power. So power, we need I think it's this one. Nope, that's amps. This one. Volts squared over ohms equals power. Go back. Oh, too far. 120 volts divided by 2,000 ohms equals 0.06 amps. So if we just do 120 divided by 2,000, is that what he's doing? That's exactly what he's doing. Stop going forward. There we go. 120 volts times 0.06 amps equals 7.2 watts. That one I do understand, because I finally understand volts, amps, watts. Ohms is a new thing. That's what I'm learning today. So 7.2 watts equals dim light bulb. Alright. I think I understand this. Now you do it. How many amps is the bulb using? How many watts is the light bulb? Why is it brighter than the previous light bulb? So it's using 144 ohms. 120 volts. So we should be able to do 120 divided by 144. This should be using 0.83 repeating. So 0.83 repeating. That's how many amps. So if it's that, so we do 0.83. We're just going to do that times the 120, 99.6 watts. So that's like a 100-watt light bulb. Answers. The bulb is using, yes, 0.8333 amps. Using the equation of 120 volts divided by 144 ohms, you get that answer. That's exactly how I got it. Perfect. The bulb is a 100-watt bulb, using 120 volts multiplied. Whoa, that's not how we got it. How did he do this? The bulb is a 100-watt bulb, using 120 volts. Okay, yeah. Multiplied by 0.8333 amps of current equals 100. So that's exactly how we got that. This bulb is brighter because less resistance allows more current flow. More current flow equals more electrons, equals more power, equals more light. All makes sense. We are on slide 20 out of 167. So far, I'm not falling behind. AC is alternating current. So it goes positive, and then 0 volts, and then it's negative volts, and then it's back to 0. So one cycle is one hill, one valley. I do understand AC/DC. It alternates between positive and negative, so it's called alternating. Get it? Up, down, up, down, up, down, up, down. Yes, on the same path. DC is direct current. DC doesn't move back and forth. It is a straight line. Direct, straight. Get it? I don't understand that part, but sure. We are also going to do this real fast. There we go. DC is direct current. Direct current. So that's 0 volts, I would assume. And this is X volts. DC doesn't move back and forth. It is a straight line. Direct. Straight. Get it? This is also DC, but a crappy one. The more straight the line, the better. We use capacitors to make it as straight as possible. Alright, that makes sense. Laptops use DC. Computer processors are based on transistors and binary codes. Ones and zeros, on and off. We've all heard that. In order for you to have a 0 or a 1, you need a valid reference. So we do not want alternating current for our power source. Getting a computer processor to work using AC would be like trying to play Jenga on a roller coaster. We do not want to use AC for powering most parts of laptop and cell phone circuits. We want flat, steady voltage. This makes sense. Think of ground as a black hole. Whether a voltage is 1000 volts or a negative 1000 volts, when it gets to ground, it becomes nothing. Ground is a reference by which we measure other voltages. For our purposes, troubleshooting laptop and cell phone circuits, ground is always 0 volts. Makes sense. For our purpose, troubleshooting laptop and cell phone circuits, ground is the absence of voltage. Electricity does not enjoy existing. It wants to return to 0 volts, so it would always seek ground. This is a symbol for ground. It's like an arrow pointing down. That's how I've always seen it. Well, I mean, it could be pointing anyway, but it always looks like an arrow that's dead. Resistors resist the flow of current. Okay, that makes sense. You'll have the same amount of voltage on each side of an individual resistor. So we're going to have the same voltage on both sides of a resistor. You have less current on one side than the other side of a resistor. Resistance is measured in ohms. Higher resistance equals less current on the other side. Higher resistance equals less power. Lower resistance equals more power. Okay. This is a symbol for a resistor. It's a squiggly mark. How resistors often fail. I resist pass power properly. I don't, and nothing comes through. Okay, that's pretty good. Capacitors consist of two charged plates with an insulator sitting between them. Alright, so it would be like metal, and then it would have some type of insulation, and then another metal. Or, it can go that way. It's the same idea. Capacitors can be used as a battery, retaining electrical charge. Capacitors are used to smooth out a signal. Capacitors pass AC and block DC. When capacitors open and begin passing DC as well as oh, whoa, that's a weird sentence. When capacitors open and begin passing DC as well as AC, you get a short to ground, which is how many logic boards fail. Okay, so when he says open, it doesn't mean a good open. I think that means fried open. You typically have the same or near identical voltage on both sides of a resistor, but less current flow. So this is a 1 kilo ohm resistor. So 120 volts. So this wire has 120 volts. 1 kilo ohm resistor. So now has 120 volts near 0 volts. It's because all of our amps are gone. The light bulb is on, but very dim to ground. I think that's because all of our amps are gone. I think this is how that works. So we have C4510. Hi, I'm a capacitor. So this is what a capacitor looks like. So far we have... I gotta write these down. Doop. So that's ground. And then we have a resistor. I'm sure that's not how you spell it. Do I get my custom shape? Which looks... that. Okay, we'll just do like this. Get our custom shape. And then we can just erase this part. Good enough. And then we have, what was this one? Right, capacitor. Which looks like that. And let's see if I can spell capacitor. Capacitor. That's not right. C-A-P-A-C-I-T-O-R. There we go. Little handy dandy thing. Woohoo. Hi, I'm a capacitor. Perfect. I'm a capacitor letting AC through. That's the AC current. It goes hill, valley, hill, valley, hill, valley, hill. I'm a capacitor blocking DC. DC dead. Cool things we can do with a capacitor. Knowing ground is where electricity will always go given a path. Whoa. Knowing ground is where electricity will always go given a path. Knowing capacitors can only pass AC waving, not DC flat. We can take a waving current and make it flat by putting a capacitor to ground on a power line. We manipulate the electricity by only sending the part we don't want away. This is all about manipulation. How capacitors often fail. I'm a capacitor. I only capacitate. Watch me laugh at DC as it tries to pass through me. Okay, so often they just let everything through, and that's how they fail. Short circuit is when a signal or voltage is stopped before it makes it to the final destination. Short referring to its trip being shorter than it should have been. A short can be caused by poor soldering that bridges 2 points together, or a failed component that is tying two signal power lines together that should not have been tied together. A short to ground is when a pathway to ground exists that should not. Example of a working circuit. Red line signifies path of electricity going to system. Happy. I ain't even going to pretend to know what this circuit is. Example of a short to ground. Well, let's go back real fast. Okay, so there's a ground there. Those are capacitor. Well, that's a capacitor. That one has a turn on it. Not 100% sure. But then, yeah, it sees that this is shorter than whatever that is. Red line signifies path of electricity. C7045 went bad and it's acting as a wire. Okay, so it's just a wire. Oop, forgot my lid. And this one right here, C7045, this capacitor went bad. So instead of it having to go through whatever this is, it sees that this is just a wire to ground. Circuit ends. That's a big blank spot. Short before power can flow to system. Knowing that, we love using capacitors to smooth out signals. Capacitors to ground on a line help smooth out that line. Capacitors can fail in a manner in which they turn into a wire. This can produce a short to ground. Woo! An inductor. Alright, we're on slide 41. How many minutes are we into this? 24 minutes. Let's go a little bit longer. An inductor resists quick changes in current. Alternating current has changes as it waves back and forth. An inductor is handy in helping turn AC into DC. An inductor is useful in keeping high frequency noise out of a line. An inductor cannot send current out quickly if a sudden demand of current comes up. So, what will it send if quickly shorted to ground but voltage? Well, that doesn't sound good. More on this later. This is the symbol for an inductor. Alright. So what we're going to do is we're just going to do, oh, come on, let me grab you. And we just, there's an inductor. Put a little line. I'm going to move this so I know how to spell inductor. Inductor. Finding a short. We have 5 happy caps on this line. The line works great. So here's where it comes in. We got a whole bunch of capacitors. I guess the curvy thing doesn't, unless that's indicating which way. I don't know what this curvy part means. If you do, that'd be great to know. So this one looks like it just goes doop boop. Oh, it has to. I don't know how this one works. Until one day, water is spilled and a cap explodes. C7544. Yeah, this thing is this one. It's now sending all the voltage to ground. So this capacitor explodes and ding, goes straight through. So I guess these are just capacitors. I don't know what the bend means. Measure each cap, right? Many will turn on their multimeter to capacitance or resistance mode and measure each cap. This will not work. Can you guess why? Because it's just letting everything through, so it's just going to keep going around this. So if you measure these, it's just going to go whoop, and if you measure these, it's just going to go whoop. If you measure this one, it's just going to go whoop. That's my guess. C7544 is the bad capacitor. Let's assume C543, C7542, and C7541. Okay, imagine all the other capacitors are working in perfect condition. We take the multimeter and place the black probe on pin 1 of C7543 and the red probe on pin 2 of C7543. The meter says 0 ohms of resistance. Why? C7544 is the culprit, not 43. What is going on here? And he's already marked it. So yeah, it's going to do that because it can find this short rather than seeing that. Whoop. Keep forgetting I can't scroll. The meter measures resistance by sending out a voltage and measuring what comes back on the other end. Since all these capacitors are on the same line, you get the same measurement reading in a cap. C7544 is providing the line a path to ground. Since all the other ones all share a line with the bad one, they will all measure the same if they are still soldered onto the board. What do you do now? Go back to the light bulb example. Do brighter bulbs make more heat? Yes, they do, the majority of the time. The lower the resistance in a circuit, the more power it will use. More power usage equals more heat. More heat equals hotter. If a capacitor is passing a lot of energy, it is hotter. We might now have a method to figure out which one is bad. Oh, I know where this is going from watching his videos. We can use heat for short detection. Whichever component is warmer is likely the component that is short-circuited. We can use freeze spray to help us detect the shortened component. Wherever it evaporates first is warmest. We can also put alcohol on the board, which is cheaper and evaporates quickly. What is a transistor? To keep it simple, a transistor is a transforming resistor. Okay, a transistor is a resistor whose value can change. If you're an electronics engineer major, yes, they are not linear devices. MOSFETs have 3 tabs: source, drain, and gate. Power flows from the source to drain, depending on the voltage at the gate. Okay, so this is like the, what's it called? I can't think of the name. 99.9% of the time, we are looking at MOSFETs, not other type of transistors in a laptop. and cell phone circuitry. Alright, so far so good. Types of transistors we care about. P-channel MOSFET, gate is lower than the source. N-channel MOSFET, power the source. Higher or equal to. So it's P. So we have a whole line going through, and P is lower, and it's letting power go through. It's low. It's a P-channel MOSFET because the gate is lower than the power going through. But if the gate is higher than the power that's going through, then it would be an N-channel. What voltage is present on the drain when 12 volts is on the source and the gate of this MOSFET? What voltage is present on the drain? So we need to figure out where the power starts. So here's the source, obviously. What voltage is present on the drain? So here's the drain. When 12 volts on the source and the gate of this MOSFET. So this is the MOSFET. Okay. So this square is the MOSFET. This line is the source. This is what's going in. This is the gate, which is right here holding it. So what voltage is present? So it should be 0, because if 12 volts are going in, no, it should still be 12, right? Because the gate's either open or closed. It's not only letting a little bit amount in. So if it's equal to it. So it's going to either be 0 because it's closed, or it's going to be 12 because it's open. And I don't know how to tell I don't know how to tell if it's open or closed. What voltage is present on the drain when 12 volts is on the source and the gate of this MOSFET? Yes, it's either going to be all or nothing, right? But I don't know how to tell if it's... Alright, we're going to assume all, because I believe he said that it's more often that type. Oh, it has 0, I was wrong. 0 volts. A P-type MOSFET opens when voltage on the gate is lower than what is present on the source. Schematic claims 4.5 volts. But there's always 5 volts there in the real world. Schematic is not always right. Alright, well, how do we know that this is a P gate? Or P-type? I don't know. Alright, we'll take the loss. I don't know. Oh, channel. P-type. There it is. Duh. Alright. N-type would have it at 12. Am I opening and letting power through, or closing and not letting power through? Remember, I am N-channel MOSFET. So here is the MOSFET. So this is 3 volts. LCD backlit disable. Hint. Ground equals 0 volts. So it's closed. It lets power through. N-channel MOSFET lets power through when the gate voltage is higher than the source Ground is 0 volts. If there's 3 volts on the gate, then it will open. This will send whatever is on the drain to ground, which will cause 0 volts to be on the drain. That's super confusing. Reminder, what is a voltage divider? Got 12 volts here. Here's a MOSFET. Don't know if it's a P or an N. It's letting 5-volt gate. Here's 5 volts here. And it's sending 5 volts that way. And it's ground this way. So this somehow divides the voltage from 12 volts to 5 volts. What if we used a transistor to control the voltage divider's path to ground? We could then control whether the voltage divider works. Being able to control that voltage divider, we can then control backlight being on or off based on signals from other parts in the machine. So here's 12 volts comes in. This P-channel MOSFET is letting power through since gate voltage is below source voltage. There's gate, source, drain. So it lets it through because the source is higher than the gate and it's P-channel, so it sends all of it through. This voltage divider is now working as a voltage divider since it has a path to ground. Oh, there's a This dual N-channel MOSFET is letting power through since gate voltage is above source voltage. Alright, so it's 12 volts. Goes through this, makes it 5 volts. I know because this is 5 volts here, so this is all 5 volts here. This theoretically still stay 5 volts, I'd assume. But then 5 is more than 3, so... Oh no, this goes through this again. I don't understand. So this goes from 12 to 5. How much does this take away? Because it has to go from 5 to something below 3. So I guess it'd be like 2. And then 2 would be lower than 3, so it lets it through. And this is another N channel. So the gate is higher than the source, so it lets it through. Now it's ground to 0. What is a diode? A diode only allows power to pass in one direction, often used in boost circuits, where voltage at the end is higher than voltage at the beginning. This is a symbol for a diode. Let's go and draw that in here. So we got a line, called a diode. A voltage divider steps down a higher voltage to a lower voltage. A voltage divider is a series of resistors between a higher voltage and ground. A voltage divider is inefficient but cheap, used for things that do not have high current requirements. So 12 volts. And it goes through the wavy line, which if we remember is a resistor. I guess it resists 200 kilo somethings. Let's see, here we have a resistor between a high voltage source, 12 volts, and the intended destination, and then another resistor between the intended destination and ground. It is turning 12 volts into 3 volts. So we have 12 volts. It goes through this to make it 3 volts. And then it sees ground over here. So it tries to go through this one, making it 0 volts. And then we have 3 volts that can shoot off this way to go to ground and whatever that is. Resistance of resistors will set the voltage. Allows the enable pin of this backlight IC to get 3 volts whenever PP bus SW LCD backlit underscore power is on. If you sent 12 volts to the enable pin of the backlight IC, it would die. Good thing we have a voltage divider. Alright, so that's backlight enable. Now on to the fun. Now that you have basic knowledge of what electricity is, we can go on to basics circuits. Get food first. Alright, is this the stopping point? I think this is the stopping point. Alright, we're going to stop here on slide 59. And we'll do another stream later on more slides, but we're like a third of the way through. Oy. Again, if you want to get this for yourself, I will link it in the description. Here's the first page. Otherwise, so far, I understand 94% of it, I would say. A couple slides in there got me confused, but I think I'm still ahead of the game. Ooh, until next time. Have a good one.